Hello everyone, welcome to this new video. So in this today's video, we'll be solving the problem Vertex cover. So this is a hard level problem and it's the problem of the day on Geeks for Geeks today. So before we proceed further, I would like to take a moment to mention about my WhatsApp channel. So in that particular WhatsApp channel, I'm posting about off-campus opportunities. Either it might be placement or internships. So it will be covering the batches that I'm covering is like first year to fourth year and also experienced people. So whoever is like willing to or seeking for off-campus opportunities can consider joining that particular channel. So the link to the channel is given in the description. You people can even go through it once in your free time. So let us go through the question now. Vertex cover of an undirected graph is a list of vertices such that every vertex not in the vertex cover shades their every edge with the vertices in the vertex cover. Okay, so this might be complicated at the first instance, but we'll be understanding it with the help of example through the in the notepad. Okay, in other words, for every edge in the graph, at least one of the endpoints of the graph should belong to the vertex cover. Okay, and you will be given an undirected graph G, and your task is to determine the smallest possible size of a vertex cover. That is the question. So these are some of the examples given, and this is expected time complexity and space complexity, but we'll be using another sort of solution. So these are the constraints. Okay, now let us understand the question deeply. So this is the example that I have taken. Okay, so let me be honest. I means given this task as to solve 3 to 4 months before, and I was not able to solve this because I was not able to get the intuition first, and even the code I was not able to frame it properly. But after referring to a lot of articles and all, I got a complete understanding of what is the problem asking us and how do we actually solve this, right? So with that experience only, I'm solving this question. I have solved this question today and also explaining the solution, right? So let us assume this is the graph that has been given. Now what is the vertex cover of this particular graph? Okay, so vertex cover in the sense like that in the vertex cover, let us assume this is the vertex cover A, B, C, D. Like these are the vertices. Let us assume A, B, C, D are the vertices. Okay, so with this vertices, okay, with this vertices considering, you can traverse all the edges of the particular graph. Okay, with these four vertices, you can traverse all the edges, means you can actually visit all the edges. So what do I mean by that? Let us take an example of this particular graph. Let us assume I'm considering this 1 6 edge. Okay, so the edge that I've considered now is 1 6. Okay, 1 6, let us assume, or I'll write it in this fashion so that it will be understandable. So 1 6. So if I consider 1 6, what are the edges that are connected to 1 4 and 2? What are the edges that are connected to 6 7? So I need not evaluate these edges. I need not consider this 6 7 1 4 1 2. Why? Because I've considered the edge 1 6. From 1 I can visit 1 4 and 1 2. From 6 I can visit 7. So I need not consider these edges again. Okay, I should only make sure I'm like, according to the question, like vertex cover in the sense all the vertex can also be there, 1 2 3 4 5 6 7 8, all the vertexes. Like this is also vertex cover, 1 2 3 4 5 6 7 8, isn't it? Because from each and every all these edges, we all these vertexes, we can cover the whole graph, but we need to make sure we take the least possible. That is the question they're asking, least possible size. Okay, least possible size, that is our ultimate goal. Fine. So because once we have considered 1 6, so we can get 1 4, we can get 1 2, we can get 6 7. So we need not worry about these particular edges 1 4 6 7 and 1 2. Now consider this particular 2 3. Okay, let us assume I'm considering this edge 2 3, edge 2 3. So if I'm considering that particular edge, what are all the edges I need not worry about? 2 4 I need not, okay, I'll be putting it with blue ink, that I need not worry about. So white ink, that I'll be considering it. Okay, so 2 3 if I consider, I need not worry about 2 4, I need not worry about 4 7, I need not worry about 3 5, because 2 3 to this vertex 3 we have 3 5 edge, and to the vertex 2 we have 2 4, and we have this particular thing, not 4 7, sorry, not 4 7, we have this 3 8, 3 8, right? That is the thing. For vertex 3 we have 3 5 and 3 8, and for vertex 2 we have 4, right? So we have covered all the edges, like 2 4 3 8 3 5, we have covered them, so we need not worry about them. That's the reason I've pointed them out with black, like blue ink. Okay, now consider another edge. Let us assume I'm considering this 4 7. So if I'm considering that 4 7 edge, so do I need to like what are all the edges I need not worry about? I need not worry about this particular 7 8, right? I need not worry about that particular 7 8 because I've already got that I've connected with 7, so I need not worry about it. So this is what I'll black it out, I mean blue it out. Okay, and now what is the other thing that we have left? 5 8. Okay, so if I consider this particular edge like 5 8 5 8, so that means I've like I need now I've ultimately covered all the edges, right? There is no more, there's no edge that has been left out that hasn't been colored yet, right? Some of them have been colored with white, some of them have been colored with blue, none of them has been left out. So we have completed the whole traversal. So the vertex cover in this case is vertex cover in this cases, like vertex cover in this cases, you can take 1 2 4 5 or 1 2 4 8 or 1 6 3 4 5, whatever, take any one vertex from each edge and put that into your vertex cover. Okay, so that is your final answer. So with this what can you understand? So with this set of vertices you can visit all the edges. Okay, you can visit all the edges, adjacent edges, but if you're trying to minimize this, like if you're trying to identify or discover a vertex cover of less than this size, like less than 4, maybe 3 2 1, that is not going to work out, because with vertex cover less than 4, that means if you're trying to find 3 vertices like x y z with which you can traverse the whole graph, is that possible? I'm leaving that as a task to you people. Okay, so try to identify if you can find x y z. That is not possible, I'm telling you right now only, but if you are very curious you can try. So because there is no way that you can actually traverse all the adjacent things with just 3 vertices, right? So that's not possible with in this following graph. Okay, so you can even try that out. So the least possible size is 1 2 4 5. So with 1 2 4 5 we can traverse all these things, or if you consider 6 3 7 8, even that is the same thing. So what do you like, this is the least possible vertex size. Okay, vertex cover size. Okay, I hope I'm able to understand, I able to make this concept very clear to people, like understand the question, what they're actually asking. So now let us, I'll just erase this stuff. Okay, I'll just erase this stuff. Okay, now how do we frame the approach? Okay, how do we frame the approach? So the approach is, we are, the ultimate goal for us is to, find the minimum possible minimum possible size of vertex cover. Okay, minimum possible vertex cover. Okay, vertex cover, this is our ultimate goal, now if you can clearly observe, so in the previous case what did we see? 4, we have got the vertex cover, okay, vc, or I'll just write with vc, the size of that to be 4. Now if I say vc to be 5, is that a valid answer? Yes, it is a valid answer. Like if I say the vc is also 5, vc can be 6, vc can be 7, vc can be 8, I'll say that all the vc can be also be 8. Yeah, that is also fine. But okay, if I say vc to be 3, that is not fine. Why is that so? Because with 3 vertices you cannot traverse the whole graph, but with 4 vertices you can traverse, with 5 vertices you can traverse, with 6 vertices you can traverse, with 7 vertices you can traverse, with 8 vertices you can traverse, isn't it? That's what we have seen. So vc is the 4 is the least possible. Okay, least possible. Before that there is nothing possible. Now, are we not getting an intuition of binary search here? Isn't it? So it's like the maximum possible is 8, and the least possible, okay, least possible is 4, that we have identified, but we can consider the lowest possible to be one vertex, like any one vertex. Like if you are in an illusion of traversing the whole graph with one vertex, this is the least value and this is the highest value. Now you will be taking the binary search among this 1 to 8. So what is the first middle term that you can get out of 1 to 8? Let us assume it is 4. Okay, so sorry, 8 plus 1 9 by 2, yes, it is 4. So now we will be checking with 4 it is possible to traverse the whole graph with 4 number of vertices. We do not know what exactly the vertices are. Okay, we do not know that, we need to generate, right? So we do not know what exactly the 4 vertices that we are going to consider, but we are going to consider 4 vertices. That is what we know. Okay, we are going to consider 4 vertices. With that 4 vertices, is that possible to traverse the whole graph or not? If it is yes, then we will excuse me, then we will try to confine or minimize our search range from 1 to 4. Okay, now we'll be greedy, and we'll try to search if in case on 1 to 4 do we find anything. If not, like when at the end of the day, if we do not find, this is what we will return 4. And also in the, if we are not able to, if we are not able to, you know, make sure with 4 vertices we have traversed the whole graph, then we will have our search range to be this. Okay, so it's a pure conventional binary search, isn't it? From 1 to 8, this is the low, this is the low, this is the high. Okay, from in this range itself we are checking so what the number of vertices. Okay, so this is the binary search. So I hope you people have understood. So the very first step for this approach is binary search. Okay, binary search on range or answer. Okay, on answer or range. Okay, so anything is the same. So binary search on answer or range. So means basically we are having 8 vertices. Now we are trying to take any vertices, any k vertices out of it, and we need to make sure that k is as least as possible. Okay, so in this case, in this particular case, the k turned out to be 4, isn't it? 4 vertices is the least thing. If we take k equal to 3 or k equal to 2 or k equal to 1, you cannot traverse the whole graph, that is for sure. So if you can consider only k equal to 4, that is the least possible k that you can take and traverse the whole graph, right? So that will be coming to binary search. Okay, so this taking of k, like k equal to 4 or 5 or 7 or 6 or 1 or 2, all these things can be done by binary search. Okay, number of vertices. So this actually solves the problem of number of vertices we need to be considered. Okay, vertices, number of vertices to be considered. Okay, now what is the second task? What are the vertices? Okay, what are the, let us assume we are considering k vertices out of here. Okay, now let us assume we are considering k vertices out of this. What are the k vertices? Okay, what are the k vertices? So what are the k vertices that we are going to take? Now here we have the technique called, Gosper's hack. Okay, Gosper's hack, Gosper's hack. Okay, here Gosper's hack is the second part of this thing. Or let us, I'll just remove this. I need not I shouldn't confuse you people. Okay, so what are the k vertices? How are we going to do this? So we are going to do this with bit manipulation. Okay, bit manipulation, bit manipulation. So how are we going to do the bit manipulation? So total vertices, how many are there? So I'll explain it in a grassroots level, need not worry about it. Okay, I'll explain it at grassroots level. So how many vertices are there in total? N vertices. Okay, so like we will put a binary like this. So in this case itself, let us assume there are 8 vertices, right? In this case, 8 vertices are there. So 1 2 3 7 8. Okay, so we have considered 8 bits like this. Okay, 8 bits like this. Now very first k, like applying the binary search, applying the first step, what are we going to get the k value? Because k equal to high plus low by 2, that is what we'll be doing, right, in binary search. So 8 plus 1 by 2, that is actually equal to 9 by 2, that is actually equal to 4. So k equal to 4, that means we need to take 4 bits. So how are we going to do is, so each bit represents the vertex value. Okay, so this is first vertex, this is second vertex, this is third vertex, this is fourth vertex, this is fifth vertex, this is sixth vertex, this is seventh vertex, and this is eighth vertex. Okay, now if I'm putting 1 year, 1 year, 1 year and 1 year, that means I am going to consider the vertex cover as 7 5 3 1. I hope you people are understanding this. If I'm considering, I'm considering to put 1 in this particular, you know, column, like at seventh position and fifth position, at third position and first position, that means I'm considering the following vertices in my vertex graph and in my vertex cover. Okay, so this is what I'm considering. If okay, I'll just take this off. If I'm putting 1 year, 1 year, 1 year, 1 year, that means I'm considering the vertices to be 8 4 3 2, because at corresponding to 8 we have 1, corresponding to 4 we have 1, corresponding to 3 we have 1, corresponding to 2 we have 1. This is the vertices I'm considering. Okay, so now I hope you people have understood what are we trying to do, because now we have got k to be 4. Okay, k to be 4. Okay, our first binary search trial starts with k equal to 4. So my primary job here is to find out all the 4 vertices combination that are possible. That means out of 8 vertices, I need to consider 4, any 4. Okay, any 4. That might be this 4, or that might be this 4, or might be this one, this one, this one, this one. N number of possibilities are there, isn't it? So what is that n number of possibilities? That is basically 8C4, because out of 8 available choices, you need to pick any 4. Okay, you need to pick any 4. That many number of vertex covers will be possible. That number of choices are possible. Okay, so if I put 1 1 1 here, I'll be getting 4 3 2 1. Okay, if I put 1 1 1 1 here, I'll be getting 6 5 4 3. Okay, so these many possibilities I'm getting. Now for each possibility I'll be checking. Okay, so once, I hope you people have understood how are we getting the possibilities, what are the exact possibilities. Okay, so in this only there is a second part. Okay, so after this, so I'll be leaving it as a third part to you, I mean third part here. So fourth part here, what is the third part? Now let us assume you have got a particular combination. Let us assume out of 8 vertices you have chosen first, second, third, fourth vertex. Okay, so now how do you check whether it is a valid vertex cover or not? So you will be traversing from this particular, from these vertices. Okay, and check if you visited, check if you visited all the edges. Okay, if you visited all the edges, okay, all the edges, so you will be doing this calculation. Okay, so how do you, let us assume this is the combination that I've got 1 2 3 4. So I'll be traversing from 1 to whatever the edges that I have connected with 1, and I'll be traversing to 2. I'll be standing on 2 and I'll see what are the edges that I've connected with 2. With 3 I'll check, with 4 also, I'll check. Now if in case the total edges that I've visited after combining all these things is equal to the number of edges in the graph, that means I've got the required answer. That means this is the valid vertex curve. Okay, this is a valid vertex cover, right? Vertex cover. I hope you people have understood this. So if I take a particular combination from each and every vertex, I can just check if I am able to traverse all the edges. So from 1 I'll be having x number of edges, from 2 I'll be having y number of edges, from 3 I'll be having z number of edges, from 4 I'll be having w number of edges. And if this x plus y plus z plus w is equal to total number of edges in the graph, that means yes, it is a valid vertex cover. I hope you people have understood. Okay, now this is also fine, this is also very good. We have understood everything that needs to be there. Okay, now we have got a particular combination 1 2 3 4. Now what is another combination out of 8 that we have considered? So like this is how it is, right? So this is how it is, and we are putting one here. That is the reason of we have got 1 2 3 4. Now what is another combination? This is another combination. Okay, this is also another combination. Like there are various combinations, 8C4 combinations are there. Now how are you going to get another combination from the starting combination? This is where like going to like, or not going, framing and another combination. Okay, framing and another combination. So this is where we'll be using the technique called Gosper sack. Okay, Gosper sack. So this is where we'll be using the technique called Gosper sack. Okay, so from a given combination like 1 2 3 4, I need to generate another combination and again check on it. I need to generate again another that particular combination. Again I need to check, and again I need to generate another combination. So it's like a train, right? So from 1 2 3 4, I need to generate another set of combination. Check on it, again another combination, check. So this process goes on, until and unless you find some combination from where you'll be returning true. Okay, this process goes on. Now this generation of this particular thing, this generation needs Gosper hack. Okay, so from 1 2 3 4, how are you going to get another particular combination? From this particular combination, how are you going to get another particular combination? This is where we'll be using Gosper hack. Okay, so how are we going to use that Gosper hack? So the detailed thing is given in a document. Okay, I've attested the link to the document in the description as well. Now also I'm going to explain that. Okay, so if I just take this, so this is the document I'm talking about. So sorry, not Gosper sack, Gosper sack. Okay, sorry for that. So this is the code for Gosper sack. Okay, let us assume this is the thing that we have taken, the combination. Okay, this is the combination that we have taken. Let me reduce the thickness. Okay, so let us assume this is the combination that we have taken, and from this combination getting another combination. This is second combination. Okay, this is second combination, this is second combination, this is first combination. Okay, this is first combination, this is second combination. So generating this combination from this combination is known as the Gosper sack. This is the technique that we'll use. Gosper sack is the technique that you're going to use to generate that. So how are we going to use the Gosper sack? So let us take this example. Okay, n bits, k set bit equal to 1. So let us assume n equal to 6. In our previous case we have taken n to be 8 and k equal to be 4. Now let us assume we have taken n to be 6 and k to be 3. Let us minimize our work, but algorithm remains the same, right? So n equal to 6 and k equal to 3. So what are the all possible combination? 6 is C3. What is 6 is C3? 6 into 5 into 4 divided by 3 into 2 into 1. So that is actually equal to 20, isn't it? 20 combinations are there. So if you check first combination, second, third, fourth, fifth, sixth, 7 8 9 10 11 12 13 14 15 16 17 18. Missed something, like in here the total combinations are 7, but I've only counted 7. Means 6, and here also the total combinations are 7, I've counted only 6. Okay, so plus 2 20, right? I hope you people have understood. So what are the combinations that we are taking? 00011, okay, and here 10111. So it's just that the different arrangements of three ones, right? Different arrangements of three ones. That is what we are saying. So here another arrangement of 111. So another arrangement of 111. So all these are various possibilities. So generating them is the Gosper sack. Okay, that is how you'll be generating. So how you'll be generating? What is the procedure of generating it? So first, this is the initial combination, right? So initial combination is putting three ones. Let us assume in our case we have k equal to 3 and n equal to 6. So putting three ones at the first three places. That is our first combination. And from there we need to generate all the other combinations possible. So how are we going to generate? So this is a procedure, okay? Find the rightmost one bit, and that can be moved left into a 0 bit. Move that one bit left one position, and move all the one bits that are to the right of that bit all the way to the right. These are the two steps that you need to do. Okay, these are the two steps that you need to do. So if you consider this particular combination 00011, so find the rightmost one bit that can be moved to the left. What is the rightmost one bit? This particular thing. So move that to the left. So you'll be getting this particular combination. Okay, this is the final result. And after moving that, find the rightmost one bit. That is done, and move all the bits that are to the right of that bit to the right. So what are all the things that are there? To like this particular one, you have moved it to the left, you have got this. And what are the all the other ones that are there to the right? Keep it right only. So that is already there. So this is the final result after the first step. Now this is another combination. Okay, this is a second combination. Now how to get another combination? Again, do the same. Put this one to here. Okay, put this one here, you'll be getting this particular result. Okay, so this one have generated here 1101. So the leftmost, or I mean the rightmost one bit, that you can try to move to your left. So this is also done. Again, now this one to this. Okay, so you'll be getting this particular thing. Again, after this to this, you can move it here. So you'll be getting that one, and all these two ones, push it to the right. So you'll be getting this particular thing. I hope you people have understood. So this is the algorithm. Like, find the rightmost one bit that can be moved to the left, move it left, and then all the one bits that are to the right of that bit, move it that to the right. That is the particular way to solve this question. Now, okay, so where will you stop doing this? Okay, where will you be stopping doing this? Our total n is range is n bits. Okay, n bits. So if you're crossing that n bits, okay, so for example, this is the last combination that you can get. So after this, what is that thing that you'll try to do? Push one here and push these two ones to the right. But after doing that, you'll be getting 7 bit. Okay, n is extending to 7. That is not what we required. That n is not 7. So we must stop at this case. Okay, we must stop at this case. Once you have got this, you must stop at this case. That is the reason we have kept limit to be one left shift of n. Okay, so one left shift of n denotes the limit. So once, if your set is actually crossing that limit, once your particular combination is crossing that limit, you'll stop automatically. So this is the limit that you can have. So one less than one left shift n, that means 7 bits. If you're actually doing for 6 bits, so 6 bits it will be left shifted. So that is the thing. So that is the stopping point. After that, you shouldn't do. So how is that Gosper sack working? So that is the thing that you need to understand. So what are the 3 steps of the Gosper sack? If you can clearly observe, these are the this is the same code that I've put in the code as well. So first, take int set, and take int c. Okay, take int c, and then take int r, that to be set plus c, and then set to be this particular thing, r or set right shift of 2 divided by 3, and then r with r. So this gives the final second combination. Okay, but how are we getting this? How are we getting c? What is the value of c? What is the value of r? And what's the final value of c? That we'll see that here. This video is going to be lengthy, so it's up to you people to watch it or not. If you wanted to understand the concept better, you can continue watching it, or else you can stop it and you can forward it to the coding part. Okay, so this particular thing, okay, let us assume this is a set we have considered. Okay, 0 0 1 1 0, or let us come to this point itself, leave this thing, come to this particular set is equal to 0 0 1 1 0. Now how do you calculate minus set? Minus set is basically take complement of set and put 1. Okay, take complement of set and put 1. If you take complement of this, what do you mean by complement? Wherever you have 0, put 1, and wherever you have 1, put 0. Okay, so 0 0 1 1 0 will be having 1 1 0 0 0 1. Okay, now once you add them, you'll be getting 1 year 1 year 1 year 1 year 1 year 1 year. Okay, and now add 1 to this. Okay, so I've done a mistake. So what I've done is, okay, so okay, fine, just give me a moment. Okay, Okay, so I'll just explain this again. So if you're having this particular set, okay, 0 0 triple 1 0, take, how do you calculate minus set? Okay, so I'll be writing this 0 0 triple 1 0 here, and minus set is calculated by take the complement. So if you take the complement, you get 1 1 triple 0 0 1. This is the complement, and add 1 to it. If you add 1 to it, you get 1 1 plus 1 0, and you'll be having 1 here 1 0 0 1 1. So this is the minus set value. Okay, this is the minus set value. So this is what they have written, 1 1 0 0 1 0. Okay, now add them up. Okay, if you add them up, you get all to be zeros. Okay, all to be zeros, that is for sure. And now if you take the set end of minus set, okay, if you take the end between these two, if you take the end between these two, you'll be having this particular result, 0 0 0 0 1 0. You'll be having this particular result. So what are we getting from this? You'll be getting the rightmost bit. Okay, you'll be getting the rightmost one bit. So this is what you're giving. This means that if you actually see this particular statement, this means that set and minus set gives us the rightmost one bit in set. Okay, rightmost one bit in set, because that is what you're supposed to move, right? That is what you're supposed to move. This line alone should be added to the list of clever x, yields the lowest one bit in the x. Okay, this is for sure, because you have got this. This is the lowest one bit, right? So the next line, add c to the set. Okay, so once you have got this particular value of set, this you are storing in C. Okay, set and minus set you are storing in C. Okay, now what is the next line telling? Add that particular C to the set. So this is a set we have, this is a C that we have derived. Once if you add them, you'll be getting this value as particular R, right? 1 plus 1 is 0, 1 carried, again 1 plus 1 is 0, 1 carried, 1 plus 1 is 0, again 1 carried, and 0 plus 0 plus 1 is equal to 1. Now you found the, you actually made that particular one, this particular one, to the left shift. Okay, you have did that, you have actually transformed the rightmost one bit to your one by one step to the left. That is what you need to do. So this accomplishes the step one of the manual process outlined above. Find the rightmost one bit that can be moved left into a 0 bit. So we have successfully moved it, right? We have successfully moved it. Now what is the second task? Pushing these two ones to the right. That is the second task. Okay, so all the left is to take the other bits on the right side, rightmost cluster of 1 bits. Okay, now our task is to make sure the other two ones are there to the right side, to push them to the right. So how are we going to do it? So this is where we are doing the operation. The starting part is R XOR set. What will you do? We'll be getting from doing R XOR set. So this is the set we have, right? And this is a C we have, and this is the R we have. Doing R XOR set, so doing this too. Okay, this is what you're going to get. And now if you carefully observe, so this is the value of R XOR set, and this is the value of C. This is the value of C. So if you can actually this is what it's saying here. So how do we shift this bits over? So we want the final answer to be 0 0 0 0 1 1. Okay, we want our final ones to be in the rightmost side. So how are we going to do it? So how do we shift this bits over? Like, this is the statement. How do we shift this bits over? Recall that C is the value of the rightmost bit in the set, isn't it? We have got the value of C. Why did we get the value of C? For this reason. So in the R XOR set, the rightmost bit is stored in the set. It's stored in the C. Okay, and therefore also the rightmost bit in R XOR set. Dividing R XOR set by C moves all the bits to the right far enough to remove all the trailing zeros. Okay, so once you divide this R XOR set by C, I mean this particular C, R XOR set by C, you'll be having all the zeros that are right side to the R XOR set to be gone. Okay, it will be deleted. So you'll be right shifting like that. So R XOR set by C gives you this final value. Okay, now what is the thing that you need to do now? Because you're having extra of two twos, right? We extra of two ones, right? We need only two ones, but we are having extra two ones. So how are we going to get that? So this still contains two more 1 bits than we need. Okay, we can get rid of those by right shifting the result by two more bits. That is the thing. So that's the reason we have done right shift of two. Once we do this, these two ones also will be gone, and finally you'll be left out with this particular thing. Okay, R XOR set divided by C, right shift of two. So this you'll be getting as the final thing. Okay, and now after doing this particular thing, if you actually do the OR operation with R, you'll be getting the final combination. You need not bother about all these things, because that is above the range. We are only considering the below the range. Okay, so we will be only having these things into our consideration in our set bit as well. So we'll be having only these things into our consideration. So 0 1 0 0 1 1. Initially we started with 0 1 1 0 0. This is the first combination. From that we have ended up with getting 0 1 0 0 1 1. Right, this is the combination. combination. So okay, I did a mistake. This is not the combination that we have considered. So we have considered this particular combination 0 triple 1 0. From this we have got this particular combination. So this is how we are doing. So after calculating r's or set right shift of 2 divided by c, we have did an or operation with r to get another combination. Okay, so this goes on till we reach the limit. I hope you people have understood. This is a very lengthy explanation, but I've explained it in a very nice manner. I hope you people have understood. So this is the procedure of getting another combination starting from one combination, right? So the link to this article I'll give in the description. Please go through it. So let us go through the code now. So I've explained everything. So first one, we'll be taking this particular adjoint graph. So in this adjoint graph, it's like we are taking the edges into the consideration. So for the pair, initially this edges that has been given, we'll be taking the adjoint graph as like this. Adjoint of edges of I dot first of adjoint edges of I dot second denotes that there is an edge between 1 and 2 if it is a 1. Okay, if it is a 1. Okay, if it is a 1. So yeah, and finally we have made this particular adjoint graph, and now we'll be having this particular doing this vertex cover. First step, what is the first step? Binary search, right? This is the first step that you need to do, binary search. Once you do the binary search, you are taking out of n, take the any k value, so middle of that mid value. So in this case, if n equal to 8, we'll be taking mid to be 4. Okay, and now we'll be checking it. So this is the set. So initial combination, okay, initial combination, and then this is the limit, this is the stopping limit. Okay, and now we'll be taking a bool visited array. Okay, bool visited array, this is for checking if we are visiting all the edges or not. So while your set is less than limit, so put all the for each and every combination we are going to do, right? For each and every combination we'll be using a particular visited array. So if your set is changing, like if your combination is changing, again you need to set your visited array to be false, like all edges visited is false. Now int count to be 0 to count number of edges visited. Okay, number of edges visited. Okay, and for int j equal to 1, v equal to 1, j less than limit, j equal to j left shift of 1, v plus plus. What are we doing? The same thing that I've explained here, right? So I'll just take this notepad. So this is the thing that we are talking about. Okay, I've erased it. So if I take 8 vertices like this, 8 vertices like this, like initially j equal to 1 would be here, like in terms of bit manipulation. So j equal to 1 and this is v equal to 1. So left shift of 1, when you do, your 1 will come to here and this will be representing your vertex 2. Again left shift of 1, this will represent your vertex 3. Again left shift of 1, this will be represent your vertex 4. Like this is how it goes on, right? So this is the value of j and this is the value of v. So j is having a traversal of j left shift of 1, when v is like v plus plus. So each bit position denotes a particular vertex, right? So this is the procedure. So if like yes, for int j equal to 1, v equal to 1, j less than limit, because j has a limit till limit, and j left shift of 1, v is plus plus. Okay, and if set and j, okay, what do we mean by that? So let us assume we are taking the combination to be, so like if a particular in this thing only, I'll just erase all this stuff. Okay, so let us assume we are taking this particular combination 1 1 1 1. Okay, so what do we mean by this? This is first, second, third, fourth, fifth, 6, 7, 8. So what are the vertex curve that we are trying to evaluate on? 6 4 2 1. Okay, so whenever we have j, okay, j is like starting from 1. So if this is a set or not, you'll check. Means at this position do we have 1 or not? If yes, that means we are considering that vertex. Yes, now come to 1. Okay, after this traversal, j will come to this particular bit position. Again it will check bit or set bit at second position or not. Yes, that means we are trying to consider second vertex. Now again it will come here. Now it will check it is 0 here. So doing like end operation with this will give 0. That means we are not considering third vertex. Come to 1 here, 1 and 4, it gives 1. So we are considering that vertex. Come to 5, we are not considering because it's 0. So end operation will result in 0. So we are not going to consider. Put this here. It will it is giving a value. So it is considering. So 6 4 2 1 is a particular combination we are trying to consider. So that is how we are using the concepts of bit manipulation and j value for traversal and v value to indicate the vertex that we are considering. Okay, so for int k equal to 1, k less than or equal to 1, k plus plus, this is to check to traverse all the mean edges, all the edges, okay, to traverse all the edges. So this is the thing. If adjoint of v of k, so adjoint of v means is there a edge present with k with the vertex like k equal to 1, k equal to 2, k equal to till n vertices are there. If there's an edge between v and k, yes, if it is there, and also if it's not visited, then mark them as visited and count plus plus, because we do not want the duplicacy to happen, right? And finally, if your count is actually m, that means all the edges that we are covered, then we return true. If not, we'll return false. Okay, so this is the Grosper's hack. This is the Grosper's hack. Grosper's hack. This is the Grosper's hack. So int c equal to set and minus set, and int r equal to set plus c. Set is equal to r's or set right shift of 2 divided by c or r. Okay, so this is the whole thing that you need to do to get the another combination. Okay, so this is how we'll be moving around, traversing around, taking all the combinations possible, and finally we'll return false. Okay, I hope you people have understood this whole long procedure. It's a very lengthy video, I accept that, but I've explained each and every concept at a deep grassroots level. And for your reference, codes in C++, Java, Python are there in the description. Please go through them, and also the link to the article is also given. Please also go through them. Okay, that is also very, very important. And yes guys, so thank you for watching and sparing you a lot of time in understanding these things. It will really help you a lot in future, right? So yeah, thank you guys for watching this video. Stay tuned. And also, yeah, forgot to mention this time complexity and space complexity. So time complexity is basically we are doing a binary search, so that is log n. Okay, so I'll just write it here. So we are doing a binary search. We are doing a binary search. Okay, we are doing a binary search, that is log n. That is log n. Okay, wait, let me minimize this first. It's hanging a lot. Binary search we are doing, that is log n, and after binary search we are generating sets. Okay, combinations, different combinations possible. So that is 2 power n. Okay, like n places are there, so 2 power n combinations are possible, and for each combination we are checking. Okay, we are checking if we are able to traverse the whole graph, and that is taking O of n square. Okay, so finally it is log n into 2 power n into n square. This is the time complexity, and space is n square because we are taking an adjoint graph, right? So that's it. I hope you people have understood. This is TC, this is SC. Okay, so these are the things that are there: binary search, and then number of sets, worst case 2 power n sets, and checking, so O of n square. That's it, right? So this is all for today's video. Thank you for watching, and stay tuned.